Here I've copied the volumes that I calculated from the previous page, although I didn't do the crust specifically. You can get the idea from how I did the mantle. Now I've got those organized, and I need to calculate now the volumes. And from the lab experiment, I have the density of the material, so the density of the crust. And a lot of times I will use this Greek letter rho, which stands for density, just as V stands for volume. The density of the crust is going to be our 2.9 grams per milliliter. Density of the mantle is 3.4 grams per milliliter. And the density of the core is 7.87 grams per milliliter. And if that strikes you as going from least dense to most dense, that should be the case. When the Earth was formed, these layers were all molten and allowed to separate out due to density differences. So the crust is substantially less dense than the mantle, and then almost an order of magnitude less dense than the core. So we've got this information, and we've got our lab data, grams per milliliter. We need to get really milliliters into dimensions of cubic kilometers. Well, the one thing that you do have to memorize in this course, we're going to calculate the density of the crust in terms of cubic kilometers as opposed to milliliters. So that's going to be quite a difference in units. So if we have a density here, how do we express 2.9 grams per milliliter in terms of grams per cubic kilometer? So if we get milliliters, very much, so a lot of milliliters in 1 cubic kilometer, so it's going to be a lot of grams. Well, we know from the equation above, 1 milliliter equals 1 cubic centimeter. So I can rewrite this, grams per cubic centimeter. And to convert cubic centimeters, I want to cancel cubic centimeters out, so they'll go on top. And I'll convert to meters for now. So cubic centimeters to cubic meters, as we discussed in class, 1,000,000 cubic centimeters are in 1 meter. Well, kilometer is a little bigger. If we've got a cube that's got 1 kilometer sides, that's 1,000 meters on each side. And 1,000 cubed is 1 billion. So there are 1 billion cubic kilometers. Sorry, cubic meters in 1 cubic kilometer. Now we can go through and cancel out units just to check that we have things in the right order. Meters, cancel out meters, and we'll end up with 2.9 times 10 to the 15 grams per cubic kilometer. So that's fairly massive, but we're talking a cubic kilometer of rock. It's an enormous chunk of rock. And now we need to just say, okay, well, what's the mass of the crust? Well, our density, symbol for density again, is just mass over volume. And if we want to solve for mass, we multiply through by volume. And volume cancels out there, so we have mass equals volume times density. So the mass of the crust is equal to our volume times 10 to the 10th cubic kilometers times, I'll put that in parentheses just to separate it out a little better, times our density of the crust, and we in the same units, so we need it, and we have that here, that we just spent all the time doing. So that's times the density of the crust. And again, without worrying about the numbers, really, because it's the process here for now that's important, take a look at the units. We have kilometers cubed times grams over kilometers cubed, and our kilometers cubed will cancel out. And we end up with some very large number that, well, is 1 times 10 to the 10th. The coefficients aren't going to change. It's still going to be 2.9, and we're going to add the exponents. 2.9 times 10 to the 25th grams. That's quite heavy. Wouldn't want that dropping on your foot. The process for the mass of the mantle and the mass of the core are the same. We have here a template. You can follow that on your own, and I will post the answers shortly. So here I brought this number over from the previous page, and then calculated the mass of the mantle, taking the volume of the mantle times its density, and those numbers are filled in here. I took the liberty of just cutting through the intermediate steps and right to the answer. And the same for the mass of the core. So add it all up, we've got, so added up the mass of the crust, the mass of the mantle, and of the core, and we get a number like this in grams. In kilograms, there are 1,000 grams in a kilogram, so if we did convert that, it's most likely it would be expressed in grams, or sorry, kilograms. We want to alleviate grams, so put down the bottom of kilograms on the top. And if we have 1 kilogram, we have 1,000 grams, and that gives us 4.4 times 10 to the 24th kilograms. And although I haven't looked it up recently, that's probably pretty close. It's in the ballpark for the mass of the Earth. That's not really the ideal way to do it, but it's a way to check and reasonably close to reality. So that would be how you tackle that problem. There could be other ways, but this is the way I chose. And that concludes this segment.